You're gonna hand out with Ben. Okay. Your stuff. Okay. And let me go up there and announce really quick. Awesome. Okay. Hey everyone, we're gonna get started. So, hi, different face. I know Megan's typically here, but today it's me. Sorry. I'm Sam. I typically do the social media, so they took a picture of you. It's already on Facebook. Go check it out. But anyway, for anyone new to the audience, this is Astro on Tap. It's a special Astro on Tap. I know you hear that all the time, but it really is. This is our first annual undergrad showcase. We have two awesome undergrads. They're going to do amazing. But before we get to the talks, we're going to do trivia as always. So I'm going to put the questions up. You get 1 minute per question. We're going to go through all of them, all 10. And then we're going to go back and do 15 seconds per question. Get all your final answers in, and then we're going to start those talks. So if you want a trivia sheet, please come see our two people. We got Ben up here in the lovely hat, and then we have Ben here on the other side. So come get your sheets and pencils.
No, another one. Or I just plug. Actually, Jake, I can just plug this into the. No, do it.
All right, and your last takers. Oh, we need one more. All right, hold up. We're holding. Everyone's waiting. You got it. Starting in like T-minus 10 seconds. All right, let's get started. Here we go. Woo! Oh.
Dope. Dope.
For now, on and live. Not live. Turn them on. Who's first? Sam's first. But one stays with the you. We've got big sharks at minutes. Sam?
Yeah.
This is yours. One is
From here, how do you mute that?
right button switch between them, left button unmutes.
I couldn't figure it out.
Yeah, it is a wacky system. Now I got it.
I just told him he was going to be caught.
Rude. Picked up sound from something, I don't know what. It's picked up sound from us, the receivers making noise.
It's great.
I'm liking the Beatles. This is a good team. Like all the jokes that
run through, and then now I'm going to go back to the first one, and you get 15 seconds per question. Okay, hope you got all your questions looked at and you got final answers. So we're going to turn them back in now. Vin and Ben, lay your hands. Yeah, come turn your trivia sheets and your golf pencils back to them, please.
I'll help with the music instead.
Okay.
Okay, there we go. The computer is having issues. You're fine. Oh my god, what happened? Okay. Hold on. I'm gonna start here. Be carefully. I literally looked at it before I got here. It was fine. I think we just have a lot of cords being plugged in. You got this, computer. Come on. Okay, while we wait for that, this is your clicker boy. This is front and back, and there should be a laser on here. I think. Yeah, there it is. It says plant right here. And let's get you mic'd up, actually. You mic'd up? They already did it. Awesome. I have your... your introduction, so I'm just going to go up and be like, hey, this is Sam. And then you're welcome to start whenever you want. Yeah, we're going to do great. Alright, we have all the slides? Done?
Hey. let's get started. As always, for trivia answers, we're going to show you guys them after our first talk. And then if you win, please wait until at the end of the second talk to come up and get your prizes. But, okay. So you can mess with my view. All right. So introducing our first speaker, this is Sam. They are a third-year student at the University of Washington. They love space science and using education to give back to the community. And they're super dope because they're active, they play guitar, and they also have a leadership position in the fraternity. So I'd love to hear more about that. But I want to hear more about this specifically. So let's welcome up Sam.
Hello, everyone. Like Sam said, my name is Sam, and I'm a third-year student at the University of Washington, which means that this is the first public talk I've ever given. So come with some slack. I'm a little bit nervous. Yeah, hoping to go to grad school soon. I'll be applying in the fall, which is kind of terrifying. But that means that about this time in my career, people start asking, what do I want to study? What kind of research do I want to do? It's a little bit like the what do you want to be when you grow up question for astronomers. But I think that what I want to study is extragalactic astronomy, which means stuff outside of our galaxy. And that's kind of funny because that's literally the majority of the universe. But I'm into like the big things, the big questions, studying the entire universe, large scale stuff, all that cool thing. And kind of related, I'm doing a research project this summer at Caltech with a guy named Liam Connor, and we're going to be studying gravitational lensing, which we'll get into here in just a second. But I thought it'd be fun to come up here and share a little bit with you guys about some of the background learning I've been doing and to get ready for the topic. So let's get into it. We'll start with optical lensing. This is something that we should all be familiar with, even if not by name. But the basic idea, the basic idea is that you have light coming in, and then the light hits a lens, typically glass, and then the shape and material of the lens is going to focus the light to a point. I know we're all doing this right now because your eyes are lenses. The light's coming in, it's being focused on your retina. And if your eye lenses don't work so well, you can get extra lenses, glasses, like I'm wearing right now. And then more astronomy related, we used to make telescopes out of lenses. They're called refracting telescopes. A couple hundred years, this is how we made telescopes. And the reason we made telescopes is because lenses can allow us to see farther, which we'll get into in a little bit. We don't really use lenses anymore. We mostly use mirrors because lens telescopes have issues. But now on to gravitational lensing. So in the same way that the shape and the material of an optical lens will bend light and focus it to a point, gravity can also bend light and focus it, and this is gravitational lensing. Gravity can bend light because of Einstein's theory of general relativity, which is, honestly too advanced for me. I find it confusing, so it's more of a grad school topic. But the basic idea is that things that have mass will bend space-time. Not a basic idea at all, actually. But things that have mass will bend space-time, and light will follow this curved space-time. So actually, this image looks terrible right now. But if you imagine this plane is a 2D version of space-time, then sun is bending it, and then there's some light here that's going like this. It's following that curved space-time. And so to us, that just looks like light is deflected. And so this is what causes gravitational lensing. You can see gravitational lensing over here, where we have the source is a galaxy, so that's what's emitting the light. And then the lens itself is a cluster of galaxies, that's what's providing all the gravity. And then the light is focused back onto there. So that's gravitational lensing. We'll make a distinction between strong and weak gravitational lensing. So weak gravitational lensing is just any time that light is bent in space. And because there are a lot of things in space that have gravity, almost all of the light that reaches us is bent in some way by gravity, even just a small amount. And this is called weak lensing. When the light is bent, it'll change the image we see slightly. It'll distort it a little bit, and we call that shear. And so people can do science with this, with weak lensing. Don't take my word for it, but I imagine the way they do the science is that they literally look at something in the sky and the things around it, and they line up exactly where the things were and how the images have been bent. It sounds a little tedious to me, but they're able to do some really cool science with this, study cool things in the universe. So that's all great, but what we're going to focus on today is strong lensing, which is the more interesting case in my opinion. And strong lensing is when you see multiple images. When something is gravitational lens and you see multiple images of it, and this is typically what people think about when they think about gravitational lensing. So we have a little example picture up here. So here's the source, here's the lens object, the thing that's providing the gravity. And because it has a lot of gravity, the light is being bent. And if the light can be bent in multiple directions to reach us, that means we're going to see multiple images. Because when light comes to us, we can't really tell that it's been bent. To us, it just looks like it's coming straight. And so we see it, the image sort of projected backwards straight away from us. So the image looks like it's coming from here. So we'll see multiple images. And then this is what it would look like to an observer. So us here on Earth, we see one image, two images. Here's the source. We don't actually see that. We see the lens. So this strong gravitational lensing can come in a couple of flavors. We have doubles, so 2 images, quads, 4 images, and then the most extreme case is a ring. It's called an Einstein ring. So fun little example right here. It's a great picture of an Einstein ring. So it's a galaxy that's being lensed, and it's smeared out into a ring right here. Right. So to do strong lensing, it's a very rare thing. It's a very rare phenomenon in the universe, and that's because we really need things to be positioned appropriately. We basically need the source object and the lens object to be stacked right on top of each other, and that just doesn't happen that much in space, especially because we can't really go out there and move things around on our own. Just to illustrate this a little bit, right here we have a picture of a candle, and a person is holding up a wine glass stem. So the wine glass stem would be an optical lens, but it behaves in the same way that gravitational lens might. And just by moving the wine glass stem around, you can get the different types of gravitational lensing. I don't know if you guys can see this, but it's actually 4 images of the candle. This would be 2 images, and then here is the ring. And then the other thing we need to do strong gravitational lensing is a lot of mass. It turns out light travels pretty quickly, actually the fastest thing in the universe. And so to bend it by any significant amount, we need a lot of gravity. And that means that we're talking about the lens object being an entire galaxy or a cluster of galaxies. And then finally, we need the source to just be bright enough. Pretty obvious, but we need to be able to see it. And so typically what we're talking about is star-forming galaxies, so galaxies that have a lot of stars in them, they're very bright, or quasars. Is there anyone if you know what a quasar is? Okay, cool. A quasar is just the center of a galaxy that has a supermassive black hole in it. So it turns out most galaxies have gigantic black holes in them, at the center of them, including our own. And when there's a whole bunch of stuff falling in on this supermassive black hole, it's falling in and it's spinning around it and it's going in, it's accreting. And as the stuff is accreting onto the black hole, it emits a ton of radiation, a ton of light. So much so that the black hole is small spatially compared to the rest of the galaxy, but it will outshine the entire galaxy. So that's a quasar. And they make for great sources for gravitational lensing. And then there's a third interesting case when the source is transient. And all this means is that the light from the source is changing over time. We'll get more into this later. But this can be a quasar. So if the accretion rate on the quasar is changing over time, its brightness will change over time. And then Ross is talking about things like supernovae, so stars that die and explode will get really bright and then less bright. And then more exotic things like fast radio bursts, which are just bursts of radio waves and we don't know where they come from, or like gamma ray bursts. Yeah. So the first strong gravitational lens was discovered in 1979. You can see that down here. We knew about them for a long time before this. Einstein completed his theory of general relativity in 1915. And then in 1919, Arthur Eddington very famously proved general relativity by measuring the bending of starlight around the sun. So what they did is they set out to like Brazil, and they observed solar eclipse in 1919. And by looking at the solar eclipse, they could see stars that were near the sun. It had to be an eclipse because the sun's really bright, so you can't really see stars next to it otherwise. But they observed stars near the sun during this eclipse, and by measuring where they saw the stars versus where they knew the stars should be, they could measure how much the light from the stars had been bent by the sun. So a very famous experiment. They proved that Einstein was right, general relativity was right. That was back in 1919, and then not too long after, people were postulating that you could do strong gravitational lensing, but it took a long time until 1979 for us to actually see them. And I don't know if any of you guys can tell where the strong gravitational lens is in this picture, because I could not when I first saw it. This was taken directly from the original paper, and I stared at it for like 10 minutes trying to find it, but it turns out that it's actually just this thing right here in the middle. I don't know how they could tell that was two images, but they could. And basically they did some science. They took the spectra of these two things that they saw, and taking the spectra just means measuring how much light they're putting out over different wavelengths. And by measuring their spectra, they can determine things like what they're made of and how far away they are. And so basically they saw two different things. I mean, it looks like one. But they saw two different things, and they saw that they were made of the same stuff, and they're exactly the same distance away. So they had two options. Either it was the biggest coincidence ever, or it was two images of the same object. And they went with B, because the universe doesn't really do coincidences like that. But nowadays we've seen a lot more. So this is just a little collage of some different gravitational lenses. We can see all the different kinds up here. So right here would be a cluster of galaxies, and then a partial Einstein ring. This would be a double, so two here, and then a quad up here. And what they don't tell you when you do astronomy, when you start studying astronomy, is that it's mostly just math and equations and actually just a lot of coding. But every once in a while you get to look at pretty pictures, and that's what makes it all worth it. So right about now you might be asking, why do we care? Pictures look nice, but you should be able to do some science. I mean, maybe you're not asking that, maybe you just like pictures. But astronomers are asking, what kind of science can we do with this? And it turns out that there's three main categories of science that we can do. And the first is going to be studying the lens object itself. The second is going to be cosmology. So cosmology just means studying the entire universe. So really simple stuff. And then the last one is going to be just seeing things really far away, like this fire with this telescope. So I guess we'll do that last one first. The technical term is magnification. But the basic idea is that when something is gravitationally lensed, the light is focused onto us on Earth, and that means that more light is reaching us than would have otherwise. More light means it's brighter, so it's magnified. This is the farthest recorded strong gravitational lens. You can see it's a nice Einstein ring. It was 10.4 billion light years to it, so not a walk in the park. By no means the farthest thing we've ever seen in the universe, but given a better find, we could use gravitational lensing to see farther than we ever have before, and even just for a telescope that has a brightness limit, so all telescopes are only able to see out to a certain brightness. Gravitational lensing will allow it to see things that it normally wouldn't be able to, so that creates an interesting magnification bias, selection bias. So we take a telescope that has a brightness limit and you just look out at the sky, you're actually going to see a lot more objects than you would think you would, because strong gravitational lensing and other things will sort of bring objects into your survey. But second thing mentioned was studying the lens object. So basic idea here is that the images we see are determined by the gravity of the lens object itself. So on the most simple level, more gravity means the light was bent more, which means the images are going to be farther apart. So the multiple images will be farther apart, or in the case of the ring is going to be wider. So example right here, this is actually a double gravitational lens system, super rare. So we have this foreground galaxy, it's just like an elliptical galaxy, and then there's two Einstein rings from two different galaxies behind it that have been lensed. So pretty cool. And using these Einstein rings, these images of the source galaxies, the authors were able to determine how much mass was in the lensing galaxy. And better than that, they were able to determine sort of where that mass is radially out from that galaxy. And so these are their two data points right here. And you can see that they're clearly increasing faster than the blue line. And what the blue line is what we would expect just from looking at the lens galaxy, just from looking at the light in it. So we know that stars make light. So looking at the light, we can tell, where we think that mass should be. And so what this says is that there's a lot of mass sort of towards the outside of this galaxy that we can't see. And so some people call that dark matter. Dark matter is a super important thing to study right now in astronomy because we don't know what it is. And so gravitational lensing can help us determine the distribution of dark matter in galaxies. And then sort of keeping with studying the lens object, first we'll make a little distinction between macro, milli, and micro lensing. So this just refers to three different scales of gravitational lensing. Macro is what we've been talking about so far. So we're talking about galaxies and galaxy clusters doing the lensing. And the image separation in this case is going to be on the order of 1 arcsecond. So arcsecond is a fun unit of angle we like to use in astronomy. There are 360 degrees in a circle. There are 60 arc minutes in a degree and 60 arc seconds in an arc minute. So really, really small angle. If you were to look up at the sky and say 1 arcsecond, you wouldn't even be able to see it. And this is, the resolution limit of some of our largest telescopes. But this is the largest scale that gravitational lensing happens on. And then the next one would be milli. This is more of an intermediate scale. So we're talking about milli arcseconds image separation, which gets really hard to resolve. But the way that people use this to do science is say that something is gravitationally lensed by a galaxy, and this galaxy has like a smaller dwarf galaxy orbiting around it. We know that a lot of galaxies have smaller dwarf galaxies orbiting around them. Then this is going to cause a noticeable change in the image we see. It's going to perturb the image we see from the gravity of this dwarf galaxy. And we can use this to study the substructure of the galaxy. So another example is, say, the galaxy that's doing the lensing is really clumpy, so it has a whole bunch of mass over here and not over here, right? That structure of the galaxy is going to change the image we see. And we can use this to study the substructures of galaxies. People do this down to like the sub-kiloparsec level, which might not mean anything to anyone, but a galaxy is like 20 kiloparsecs wide, so we're studying small substructures of the galaxy. And then the third one is going to be microlensing. We're talking about micro arcseconds, so really, really small. We're talking about gravitational lensing by individual stars. And we're never going to be able to resolve this, or at least not with our current instruments. But like we talked about before, when something is gravitationally lensed, it's magnified, even on this scale. And so if you have something being gravitationally lensed by a galaxy, well, the galaxy has a lot of stars in it, and all those stars can do microlensing. And while we can't really resolve this as like an actual change in the image, all those different microlensing events are going to add up to a noticeable brightness difference we can study. And then microlensing also has another very famous application in astronomy from when people first found out about dark matter. They kind of had two competing ideas of what dark matter might be. One side thought that dark matter is just particles we don't know about, so new matter. new matter that we haven't discovered that has mass, so it does gravity, but it doesn't interact with light or anything else really. And this side was affectionately named WIMPs for weakly interacting massive particles. By the other side, that named themselves the Machos for massive compact halo object. And the Machos' idea was that dark matter is made of things we know about. It's just cold and dark and we can't see it. So their idea was that there's a whole bunch of black holes or like neutron stars, which are super dense but don't emit a lot of light, or like small brown dwarf stars that aren't really, emitting any light anymore, or just like rogue planets swirling around in space, and that was what was causing all this gravity that we see that we can't account for. And so the way that they tested this was, well, they said if there's a whole bunch of these objects flying around in space, then they're bound to pass in front of background objects and do some microlensing. So this image right here is 4 years of data from Gaia, which is a space telescope, the Milky Way, and all the little bright points are a microlensing event, right? It magnifies the background source, so you can see it as just like an increase in brightness. And so they went out and they studied these microlensing events, and they just looked out there and they counted all of them, and then they found out that there wasn't enough of them to account for all the gravity we see. So the Machos ended up losing despite themselves the Machos. And then the third thing we talked about was cosmology. And the way that we do cosmology with gravitational lensing is time-delayed cosmography. Don't ask me what the difference between cosmology and cosmography is. I don't really know. But we have the geography, so studying the Earth. Cosmography would be studying the universe. And the basic idea here is that when something is gravitationally lensed and we see multiple images of it, that means that the light is traveling on different paths to reach us. And if the light is traveling different paths, that means that it's going to take a different amount of time to get to us. And that means that we can measure a time delay between when the images reach us. And in order to measure the time delay, the source needs to be transient. So we talked a little bit earlier about transient sources, which just means that they're changing their brightness. So things like quasars and supernovae and gamma rays and fast radio bursts. But yeah, by measuring this time delay, nice little picture right here of this. By measuring this time delay, we can actually measure the expansion rate of the universe. So in case you didn't know, the universe is expanding all the time. And not only that, the rate that it's expanding is changing all the time because nothing can be simple. So measuring this rate that it's expanding is one of the most important parts of cosmology. This is called the Hubble constant, most important parameter in cosmology. And it's particularly important right now because there's quite a bit of tension with the Hubble constant. So astronomers like their beef, but again, there's two sides that are taking measurements of the Hubble constant, and they're coming up with different values. So one side is looking at cosmic microwave background, the cosmic microwave background, which is just photons that are all around us from the very earliest parts of the universe. And so this is a measurement of like really, really long time ago. And they get like 69 kilometers per second per megaparsec for the Hubble constant. And then there's another group that is measuring things closer by, so distances to supernovae in the near universe. And it's called like the distance ladder approach. And their number they're getting is like 74 kilometers per second per megaparsec. And you might be wondering, who cares? It's 5. But when we're talking about the expansion rate of the universe, this is actually really important to get this number super correct. So time-delayed cosmography provides an independent third measurement of the Hubble constant, which is super important right now to verify which one might be correct. Yeah. So you can do all this science. What's the current state of the field right now? We talked about first one found in 1979, and then I got a couple numbers up here, like 200 in 2010, several hundred in 2019, and then I couldn't find a definitive number for right now. You have to trust me on that one. But yeah, so not very many gravitational lenses. And that's what makes really doing the science hard, is because you need a lot of them to do the science, and you haven't really been able to find that many. But the increase in the number that we found, sort of exponential increase, is due to just building larger telescopes and being able to see more of these. The numbers that are listed up here are very hand wavy, because it sort of depends how you want to classify what's like an identified strong gravitational lens, because people find a whole bunch of them, a whole bunch of candidate ones, but it really requires some follow-up to determine that they're actually a gravitational lensing system. So you can kind of pick and choose what numbers you want. But yeah, and then we have another gallery down here, just of some different strong gravitational lenses. And this image is from the highly optimized lensing investigations of supernovae, microlensing objects, and kinematics of ellipticals and spirals, aka holy smokes. Might be the most contrived acronym I've ever seen. Astronomers love their acronyms. So anyway, it talks about machas and limbs, but I think this takes a day. So that was sort of the history of the field. What's next? We talked about how we just need to see gravitational lenses to do the science. Well, that's not really the issue anymore these days. We're building huge telescopes, specifically like this decade, gigantic telescopes. These are big survey telescopes, and what you do with the survey telescope is basically you just image the entire sky, and then you put out all your data and you say, "Go nuts, astronomers! Go do some science." And so the issue isn't really anymore that we're not seeing enough gravitational lenses. The issue is more that they're in the data. We just need to find them. So this nice little chart right here got data rate in bytes per night, and so these are some telescopes that are either been built or being built, and it's actually a pretty old estimate. But the SDSS, the Slow Digital Sky Survey, was really the first giant survey telescope, and back in 2000 it was putting out 200 gigabytes per night, so that's the size of an iPhone basically, but that was a lot back then, and now we're talking about 30 terabytes for the Rubin Observatory for LSST, so that's a ton of data to look through. And so you can't really do this by hand. I mean, I have read some papers about gravitational lensing where they said something like, we did a visual inspection campaign of 10,000 images. So, just some poor grad student is just clicking through
Undergrad.
Yeah, I'm laughing, but I'm probably going to be doing that soon. So yeah, we can't really do this by hand anymore. And so that's really kind of where my research comes in. So Caltech is building a super big radio survey telescope called the Deep Synoptic Array 2000. And it's supposed to be the largest radio survey telescope ever built. So we talked about a couple other giant survey telescopes that are being built. Those are going to be in like the optical wavelength, so stuff we can see. This is going to be in the radio wavelength. It's going to be 2,000 radio dishes in the middle of nowhere in Nevada. Because you need it to be far away from other radio sources. And basically, it's going to image the entire sky 16 times in the first 5 years of operating. So it's supposed to find 1 billion radio sources. So that's a lot of sources, a lot of data. And we expect in that data there to be, a ton of gravitational lenses. We expect it to increase the current sample size of gravitational lenses by several orders of magnitude. In addition to the LSST and other giant survey telescopes. So what I'm doing for my project this summer is, first we're going to do some statistics and try to figure out how many gravitational lenses we expect the DSA to see what kind of gravitational lenses, and then what kind of science we can do with those. And then the second part is going to be about building machine learning models to identify them. So talk about how you can't really hand identify them anymore. So now we got to turn to machine learning to help us out. So we got to train the machine to find the patterns for you. This isn't really that easy though, because it turns out there's a lot of things that might look like gravitational lensing. So you might say, I'll look for a ring, because the ring is a pretty typical structure in gravitational lensing, the Einstein ring. But there are also a lot of galaxies that kind of look like a ring too. So if your machine learning algorithm goes and looks through a billion sources and gives you back 150,000, well, great, it reduced the data a lot. But if half of those are incorrect, then that doesn't really help you. So it's going to be super accurate, and then it's also going to take into account all the different quirks of the telescope. So each different telescope will have its own things that it does to the image, its own instruments, and all that kind of stuff. So you got to take that into account. So yeah, I think that's my presentation.
Sam. You should emphasize
All right. Well, we will take questions. Okay, so the question was, how long is a strong lensing system observable for? And the short answer is forever. So typically it's just going to be like a galaxy or just some object lensed by another galaxy. These objects aren't moving on time scales that we care about. They are moving, but not in our lifetimes. So that light that's coming from that galaxy is going to be lensed for a long time. It's different when you talk about transient objects. So we talked a little bit about supernovae. So if it's a star exploding, then it's only producing light for so long. So you're not going to see that. Yes.
Are there objects in the sky that before we knew about gravitational lensing were observed that we now are explaining because of gravitational lensing?
That's a great question. I don't think so. Don't take anything I say as a fact, but just judging by the fact that we knew about them back in 1920, and then the first one was found in 1980, I'm going to say no. So people were looking for them before that. And then also, you just need good enough telescopes, so I don't think so. Yes.
Is the Einstein ring produced because an object that's the source is directly inside the lens as opposed to being offset?
Yes, yeah, exactly. So it's just when it's perfectly aligned.
Repeat the question.
Oh, okay. Sorry. The question was: is the Einstein ring made when the source is perfectly behind the lensing galaxy? The answer was yes.
How do you actually identify the lens in the data?
Good question. I'll probably figure that out this summer. Basically, you give the computer a ton of images of gravitational lensing, and it's able to learn what it looks like, and then it'll go look at another image, and it can classify it for you. Yes.
You mentioned that Hubble constant and there's like controversy between the two. Is there a reason why it's a constant and not like different in different areas of the universe?
That's a great question. So it's not really a constant, which is confusing. So like I said, the universe is expanding. It's expanding everywhere the same. So different areas of the universe are all expanding in the same way, but that expansion is changing over time. So the Hubble constant is the rate at which it's expanding. So the Hubble constant 1 second ago is actually different than it is right now, but we just like to call it the Hubble constant, which is the rate of expansion today, which isn't changing that much. Awesome. Thank you.
Let's do one more round of applause for Sam. That was amazing. I don't think I could have given that good of a talk as a third-year undergrad. That's fantastic. Before I release you to our intermission, we do need to go over our answers for Astron Chat. We have 2 9s and 2 10s.
Whoa!
Let's get to the answers first. So, 1. Here we go. The first strong gravitational lens discovered in the same year as the Beatles album is D. None. The Beatles already broke up by then.
Boo! We like the
Which
Beatles.
of the images showed an example of gravitational lensing? It is D, all of them. I know those will work too. 3. Who was the first person to discuss gravitational lensing in print? Not Einstein. It's B or rest. I'm not going to pronounce that, so it's okay. 4. Only visible objects can be gravitational lenses, so dark matter cannot lens anything. False. Sad. 5. How many objects are gravitationally lensed in this image? Just 1. That was hard. I was going to guess 5. Who came up with the modern system of classifying stars? It is the amazing Annie Johnson. Yeah, she's a plus. 7. Who came up with the first system of stellar classification? And John She. 8. Who discovered that the sun is mostly hydrogen and helium? Celia Payne-Gaposchkin. She also deserves some applause. Number 9. One of the dark lines on the solar spectrum. It is wavelengths absorbed by the sun's atmosphere. I know it's also hard to see, but yes, that is the spectrum. And 10. Finally, we can determine the temperature of a star by taking its spectrum. Absolutely, it's really fun. All right, so drum roll for 9. So we have in no particular order, Mike Dole. And our other 9 is Yeti. Woo! Okay. And our 10. It's been a while since you guys. We had 10 ever? This
I don't
is the
remember.
first 10 since I've been here. All right, here we go. This is big. First, Blaine. Woo! Okay, and my personal favorite of tonight's names, we have Estefia. Good job, guys. You can come get your prizes after the second talk. We have tons of different stuff. But we're going to take like a 10, 15-minute break. Go get more food. Go get more beer. Frank, do you have anything to say? Yeah. All right.
Again, Sean and I want to thank everyone for coming out. This week's special, this is our 2 years we've been in this spot. So we have stuff going on all week. So come back, say you were here tonight, you get $1 off a pint if you come back Thursday, Friday, Saturday, or Sunday. So tomorrow, live music, and there's a run club that'll be here. Friday, we have a beer and cheese pairing class. So sign up, there's a QR code up there to get your tickets. Saturday, more live music on Saturday, and Sunday is DJs playing all day. So events there, come back any of those days and say you were here tonight, get $1 off your next drink. Oh, Simcoe's up there. Oh, she saw something over there in the parked cars. Yes, so thanks for coming out tonight. Enjoy the rest of your night.
Okay, everyone. I hope you got some food and some beer. Hopefully, I think everything's we're going to get started with our second talk of the night, our second underground. So we have Ishan. Yes, they are a senior at the University of Washington. It's almost done. They're finishing their Bachelor of Science in Astronomy with a minor in Design and Performing Arts. The research has involved spectroscopic and time-domain studies of stars, particularly massive stars, aimed at preparing for big data era surveys like the Darian Observatory and as well as LSST. So in addition to research, they also mentor a couple of local high school robotics teams. They play D&D and are currently working in student advocacy. And so I cannot wait to hear more of their talk, and I'll just let them get to it.
Woo! Woo!
All right, thank you, Sam, for the open introduction. My name is Ishan. I'm going to be talking about the hidden light of stars today. So, important question before we start. What is a star? There's a lot of cliches in astronomy about ever since humans have been looking up at the night sky, we've been looking up with wonder all these points of light in the night sky. And that's exactly what a star is to us. It's a point of light in the night sky. There's also a giant one that we can see during the day sky, because as we should know by now, the sun is also a star. And really, stars are up all the time. It's just that light of one particular one that we happen to be orbiting blocks out the rest of them. And what stars are these balls of nuclear fire constantly that are producing light, and we use that light, and then we can use that light to find out a lot about what goes inside the stars, inside stars, because we can't really ever see inside a star. There's no way for us to turn on X-ray vision and look through what's inside the sun, mostly because that's not how X-ray vision works, contrary to what Superman comics would have us believe. But really, the first look to try to understand what goes on with light as a whole, perhaps should be credited to Newton, who was the first person to split light, and wrote an entire book about it called Optics. There was a longer version title. The longer title was Optics, or a treatise on the reflections, refractions, and intersections of colors and of light.
Yeah.
Very mouthful of a title, but Optics did a very good job laying the groundwork for the experimental methodology for optics and the experimental methodology for spectroscopy as a whole. I'm going to skip forward about 200 years. About 200 years to Joseph von Fraunhofer, who was the first person to actively document a complete solar spectrum and a complete stellar spectrum. At this time, there was no understanding of what was causing these spectra, apart from the fact that this was light coming from the sun or light coming from stars. It was being split apart into a rainbow, and there were little gaps showing up in this spectra, and we didn't quite know what that was doing. Then we get to this person, Angelo Secchi. Angelo Secchi was a really interesting person. He drew the most detailed hand-drawn map of a lunar crater. He drew one of the first detailed drawings of the Martian surface. He discovered 3 comets. He compiled the data for 10,000 binary stars and added 40,000 new classifications of newly classified stars under his own system, which was the first classification system for stars based on their spectra. More impressively to me, he hand drew all of his spectra. I have a very nice luxury of never having had to draw a spectra. Everything I've done just gets handed to me on a computer. I write some Python code, and it plots out a lovely, pretty graph for me. Angelo Secchi drew over 40,000 hand-drawn spectra while studying different stars, and came up with his own classification system for them. I believe the top one is the top one is the sun. The second to top one is what you call the type 1 star, and the bottom two are type 3 stars. And you can kind of see where he was like kind of drawing correlation between the different gaps. But again, Angelo Secchi lived at a time when we didn't know what was causing these spectra, and we wouldn't know for a little longer. So to maybe define what spectroscopy is, we keep throwing out this term spectroscopy. What spectroscopy is breaking light down into a spectrum of colors, and then in particular trying to see what that tells us about what that light has been passing through. So for example, on the bottom here, I have a bunch of elements. We have sodium, we have hydrogen, we have calcium, we have mercury. And as light passes through and excites each of these elements, they give off specific emissions, specific colors. There's very specific colors from a very narrow wavelengths, and we can use that to kind of create a little fingerprint for each element. And then we have like the old school spectra that you will see, like the kind that was the hand-drawn one later when we got photographic plates, also looked like that. And eventually when we got computers, that's what a computerized spectra looks like. It's giving you the same information, it's just showing you on a graph, showing flux versus the wavelength versus just wavelength, and like a graph showing color. But both of these are conveying the same information. After Secchi, there were a lot of people, like there's literally a textbook's worth of people who worked on spectroscopy between this intervening period. But there are three people I'm going to highlight. Hermann Karl Vogel, purely because he came up with one of the best free to modern spectroscopic systems, classification systems. He did a lot of work on classification. He made great leaps and strides in compiling a lot of the data. Henry Draper didn't actually come up with a classification system, but his work in spectroscopy, along with his wife Mary Anna Palmer Draper, compiled one of the biggest spectral catalogs of the time period, which the late 1800s. And then Mary Anna Palmer Draper took, after Henry's death, would go on to donate all of those spectra to Harvard, and particularly the Harvard computing group led by one Edward Charles Pickering, who, when he took over the research group, the spectroscopy research group, immediately fired his male assistants and hired his maid because he could pay women less because it was the late 1800s. So the entire reason there would soon be a bunch of women working in Harvard at spectroscopy is because Pickering could lower his budget because he didn't have to pay women that much. It turns out they were really, really good at their jobs. Wilhelmina Fleming made significant contributions to spectroscopy, made significant contributions to different classifications of stars, different types of stars, and made significant contributions correlating spectroscopy to different chemicals found in the lab. We then get to these two, Annie Joan Cannon and Henrietta Swan Leavitt, who again I'm cherry-picking two scientists from among many brilliant scientists who worked at Harvard at this period and worked across the world in this period contributing to spectroscopy. Henrietta Swan Leavitt is perhaps most well known today to astronomers as the person who was able to make the correlation between a certain type of blinking star, a variable star called the Cepheid, and how far away that star was, and using that to determine the distances to different galaxies. The first person to realize that large and small Magellanic Cloud, two satellite galaxies of the Milky Way that can be seen in the southern hemisphere, were actually how far away they were, and Leavitt's law was then later used by Sir Edwin Hubble to determine that Andromeda was actually not part of the Milky Way, but in fact a distant galaxy. Annie Joan Cannon, on the other hand, was the first to go through and take all these classifications that have been evolved from Secchi's classifications that have been evolved by Vogel, that have then were evolved by the Mary Ann Palmer, and then evolved by Pickering and Wilhelmina Fleming, and realized that there was a way she could order them by the way the signatures seemed to change in the spectrum. And she was the first person to put the stars in a particular order based on how the different spectral lines seemed to change. This was about in the very early 1900s. Norman Fleming's work would continue on especially her work on exotic stars would continue until her death in about, I think, 1911, which was the same year this graph came out. This is the HR diagram. It's called the Hertzsprung-Russell diagram. It's named after, I do not remember the first names, but American scientist and a British scientist, Hertzsprung and Russell, independently published papers that pointed out this graph. And this graph is the backbone of stellar astronomy. Some things to point out here. You have the y-axis luminosity. Luminosity just means brightness. From low luminosity to high luminosity. And then you have temperature from hot to cold. So cold is over here, and we get hot over this way, and then dim is over here, and we get bright this way. So the dimmest, the dimmest, hottest stars are over here. The hottest, brightest stars over here. The hottest, coldest stars over here, and then the coldest, dimmest stars are over here. The sun falls roughly around here. This is the main sequence. This is where most stars will spend the majority of their lives, burning during the main part of their lives. This is where some of the older dying stars tend to hang out, and these white dwarfs are remnants of stars like our sun when they die. We'll talk about them a little more. Any jump cannon would go through the letter naming system, which was initially alphabetical, and reordered them this way: O, B, A, F, G, K, F. And this seems wacky, and it seems like why didn't we just go A, B, C, D, E, F, G? Well, initially one of the intermediate systems was exactly that, but over time we realized that some of the classifications were redundant, and we combined them and then order them in terms of chemical complexity. What she didn't realize was and would be pointed out to her by one of her students who we're going to meet in a bit, was that this correctly predicted the Hertzsprung-Russell diagram. I mean, Annie Jump Cannon, almost a decade earlier, had no idea that this diagram existed or this pattern would emerge, but correctly predicted the relationship between color and temperature. More importantly, the correlation between spectroscopy and the energy that we're seeing in the flux over wavelength and temperature. So, bluer stars are hotter and redder stars are colder. And Annie's classification system correctly predicted this. And to remember this overly complicated series of letters, Annie Jump Cannon herself came up with an acronym. OBFINGUIPISC. In science communication in the present day, we also use other acronyms such as other mnemonic devices such as old bread and food gets kind of moldy. But this is Annie Jump Cannon's mnemonic device that she came up with herself over a century ago. So I will continue to use hers. But very importantly, again, Annie correctly predicted the correlation between spectroscopy and temperature and color before the Hertzsprung-Russell diagram, the main diagram that we use now, came out. So we know that I think the projector is messing up the colors a bit, but blue stars up here, yellow stars in the middle, red stars at the end. So OBA stars are blue, KM stars are red, mostly M stars are red, and then you have the yellow ones in between, like our sun. Our sun is a little G star. Yeah. So I want to really drive home the fact that spectroscopy is a way for us to ID the elements. Every element has a spectroscopic ID that we can kind of use to piece together what element we're looking at, especially when we're looking at them in distant stars.
However, for most of astronomy, missing a slide, that's fine. Most of astronomy, we really only care about hydrogen and helium and refer to the rest of the elements as metals. If you're an astronomer, anything heavier than helium is a metal. So if at any point I refer to the star having metallicity or showing a lot of metals, I'm just referring to any element heavier than helium. And the reason we know that we can mostly just care about hydrogen and helium are the most abundant elements in the universe, is because of spectroscopy. And the way spectroscopy works, and the way we see those little lines showing up, is we have light that passes through these atoms, and these atoms have a nucleus, and they have an electron whizzing around. And when photons hit the electron gains energy, and it absorbs it, and that particular wavelength of light disappears from the spectrum. When the electron goes down in energy, it emits a photon, and we get a little spike in that part of the spectrum. We get something called an emission line. And the reason we know that stars, and in fact most of our universe are primarily made out of hydrogen and then helium, is because of Celia Payne-Gaposchkin, who entered the Harvard computer, entered under the mentorship of Annie Jo Cannon, and was working through her PhD thesis as a graduate student, and put together that unlike the popular science at the time, that believed that the sun was made out of similar chemical abundances or similar amounts and ratios of chemicals as Earth was, because everything we knew about spectroscopy was based on what we were studying on Earth. So it was logical to assume that the sun was made out of similar ratios of stuff, since we're seeing all the same elements, just much, much hotter. And Cecilia Payne wrote one of the most brilliant theses, PhD theses, and basically proved step by step that stars were in fact mostly hydrogen, and with a little bit of helium, and then everything else in very short abundance. And her PhD thesis was in fact rejected. She was only handed her PhD after she put a little disclaimer in her PhD saying that there is no way these results can be real. As it turns out, her PhD advisor would then for a few years take credit, would eventually realize that she was right. Stars were mostly hydrogen. He would take credit for the discovery for a bit. Eventually, Cecilia's work came to light. We now know and celebrate Cecilia Payne-Gaposchkin as the person who truly discovered what stars are made out of. And as a person who we owe our modern understanding of stars to, stars are mostly made out of hydrogen, and will spend most of their lives fusing hydrogen into helium. This is what a typical star's life looks like. Once a star forms into a main sequence star, remember that long strike down the middle of the HR diagram, it will spend most of its life doing exactly that, fusing hydrogen into helium. As it runs out of hydrogen to fuse, it's going to start swelling up into a red giant. This will happen for a sun-like star maybe about 10-ish or plus billion years into its life. After a while, it's going to start fusing helium, and as that energy gets going, the core will contract again. It'll enter what we call the horizontal branch of the HR diagram. And then one last time, as carbon starts building up, it'll start swelling up again into an asymptotic giant branch star. And then finally, the pressure from inside the star will overwhelm gravity, and because it's a low mass star and it's boring, it'll whimper out and die. Because it's boring. What will form for some stars, not our sun, because again, our sun is more boring than the boring stars, which is good for life. It's bad for everything else. For stars of a certain mass, less than eight times the mass of our sun, more massive than our sun though, will turn into will create something called a planetary nebula, as towards the end of their life, they will start shedding some of their outer atmosphere and their outer layers. as they expand and contract. And this will create, and then in this final release of energy as the sun, as these kind of low mass stars, it's not a supernova. It's very anticlimactic. They will release this shell of gas and dust that will cause something called a planetary nebula. I think I forgot to add an image of a planetary nebula. There's some really famous ones out there. The Cat's Eye Nebula, the Helix Nebula are very common, very popular astrophotography images. Things get more interesting if you're a massive star. A massive star I'm going to define as any star greater than 8 solar masses. We will talk about 2 types of massive stars. Massive stars that are greater than 8 solar masses and less than 25 solar masses. And solar mass means mass of the sun. And we'll also talk about stars that are greater than 25 solar masses. These will start as main sequence OB stars. So remember, OB stars, the 2 hottest categories of stars in Angel Cannon system, right at the top of the HR diagram. And they have weird lives. These stars can take a myriad of different exotic evolutionary paths, but they will all end up as a red supergiant that looks something like this. These red supergiants will spend most of their lives fusing helium into hydrogen and helium. They'll fuse helium into carbon, and because they have enough mass, they can keep going. They can start fusing carbon into oxygen, oxygen to silicon. But these last 2 steps happen in the blink of an eye. Carbon to oxygen for a 25 solar mass star will only last about 600 years. Oxygen to silicon fusion about 6 months. Silicon into iron about a day. Fusing iron is really weird. Iron is a really weird element. For elements lighter than iron, you can actually get back energy by fusing it, by smushing the atoms into itself. Smushing the atoms with other atoms, you get energy back. You get energy from fusing it. For atoms somewhat heavier than iron, you can get energy back by splitting it. With iron, you tend to lose energy with both. So stars trying to fuse iron will only be able to actually fuse iron for a quarter of a second before the amount of energy iron is sucking out of the core kicks out, and also the iron fusion will suck up random neutrons around the core of the star. And simultaneously, you rip out everything holding the star up. You rip out all the nuclear pressure from the nuclear force of the stars. You rip out all the radiative pressure from the core of the star, and the star just comes collapsing inwards at a significant fraction of the speed of light. And this happens.
Whoa.
Makes the Death Star look kind of lame. And I really need to emphasize that everything we've learned about stars, including the way they evolve, is we can't really see what's going on inside. We have inferred almost all of this purely from spectroscopy and watching how different stars behave, just purely for observation. We have never seen, and we will never see inside a star, but we've done a very good job figuring out how they behave. I don't know how well this is showing up, but this is a flowchart, kind of showing you, like just the rule of thumb how you think through spectroscopy. We have different elements of here's titanium oxide. So for reference, titanium dioxide is the thing in sunscreen. Titanium oxide lines, which will tell you if the star is an M star or a really cold star. We can go through this flowchart and kind of check off and figure out what type of star any type of star is. This is a gross oversimplification, but it is based off the work of Professor Philomacy, who works in Arizona, Dr. Catherine Nugent, who is a recent PhD graduate of the University of Washington, and Dr. Brianna Smart, who currently works at the University of Washington in a paper they published in 2016. But I have added a singular test on top of all of their work, so very minor contribution. But this flowchart is a very good rule of thumb of thinking about how we can classify different stars broadly. Each of these antigen canon for each of these stars has 9 subdivisions. We're not going to bother talking about this. But what we can do is take a look at a spectra, and we can work together right now to classify the star. So titanium oxide looks like giant chunks are taken out of the spectra. So the spectra wouldn't look flat; it would look like there are giant chunks missing from it. Just be flat. Just show of hands, who thinks there's titanium oxide in the spectrum? Giant chunks missing. Okay. Cool. Thank you for being very brave. You were unfortunately wrong. There's no titanium oxide, which means we can rule out M stars. So the next thing we can look at is, I don't know why that's like that. The next thing we can look at is we can see if the Balmer series. The Balmer series is a name for the hydrogen series. So it just means we're looking for lines of hydrogen. So lines of hydrogen tend to be stronger in hotter stars. So that's the main reason we're doing that test. So currently we're just looking to see if there is a line in each of these lines of hydrogen, which there seems to be. So this one looks a little weird. This is the first line of the hydrogen series. That one looks a little weird. So ignoring that one, all the other hydrogen lines seem to be present. So are we good saying that the Balmer series is present? So aka hydrogen is present, strong hydrogen is present in this star.
Yeah.
Cool. Getting a little closer look at a really weird line. That line looks weird. It's not a straight down line that we'd expect for absorption. Something weird's going on over there, and we'll come back to it later. Now we're going to look over at calcium. So normally to see what strong calcium lines look like, they would look something like this. And I don't quite see that. So I'm going to rule that there's no strong calcium in this star. You good with that? And then finally, I'm going to do a show of hands vote. We're now looking for helium. I marked the helium lines up there. Let me know if you think there is enough helium in this star to say that there's helium present. Cool. Yes, good job. There is in fact helium present in this star. So what we've done so far, we've eliminated M stars. With that whole calcium test, with that whole like hydrogen line test, we eliminated F, GK, and GK stars. We have now also eliminated A stars. And with our final test, okay, I'm just going to give it away. There are no strong helium-2 lines, so we can hereby classify this star as a B star. In a few minutes, we have just classified a new star. So following the flowchart, we went, okay, no titanium oxide, there's hydrogen, but there's only weak calcium, no strong calcium lines. We said that there was helium present, but there wasn't helium-2 present. So we were able to eliminate everything except a B star. And in fact, this is a B star. But there's this really weird hydrogen line, and we got a couple of views of it. And to figure out what's causing it, this simple rule of thumb doesn't work. But we do know what is causing it. This is an emission star. This is a B emission star. And what's causing the emission lines is actually this disk of matter that the star has lost and has got sucked up as a disk around the star. This is a disk from the E star, and we have little examples of what we'd expect that hydrogen line to look like from different angles of seeing the star. Looking straight down, it would look like a little dip and then just a normal absorption line, or emission line. If you're looking at it at like a 45-degree angle, there would be a little dip in the middle, but it would look kind of like this, like a weird hat. And down here, you'd see the absorption line cross down, steaming through the middle, if you're looking on it edge on. So we're actually looking at the star somewhere along between scenario B and scenario C. But we actually just used the spectra to not only figure out that this was a hot main sequence star, we also just figured out that this star has a disk. And this is just based off the rainbow that we got from the light from the star. And actually, we had to thank, once again, got to thank Angela Secchi for discovering emission lines in stellar spectra. He's the first person to have ever classified a B emission star. He didn't know that, he didn't quite know what all the chemistry meant at the time, but he was able to clearly identify hydrogen emission versus absorption lines, and was able to identify that one of the stars he was looking at presented a hydrogen emission line where it should have presented an absorption line. He was able to state and was able to come up with a classification for emission stars. So, in conclusion, there were a lot of hidden stars, by which I mean uncredited people, mostly women who were not being paid as much as they should have to do the amount of amazing science they did. Even to present day, but especially in that era, in the turn of the 20th century, when a lot of this amazing revolutions in spectroscopy were happening. We can never see inside a star, but we can learn everything we need to from their spectrum. The flowchart I showed was an oversimplification, but its helpful rule of thumb is really good look inside how astronomers and scientists think about spectra as we're evaluating what a different star is and what it tells us about a star. Scientifically, this is called TY370179-01, which is the name of the star because it doesn't have a better name, is in the modern classification system of V3-5VE1 disk star. Basically translates as an early-ish or young hot star in the main sequence with a disk composed of lost mass and an acute tilt. Yeah, just a lot. That's just how. That's the fancy way of saying that. We can learn a lot from spectroscopy. And if you have any questions, I'm happy to answer them. I'm going to put the conclusions back up. Also, low mass stars are lame. I just have to put that up there as a massive star. Yes.
What's a disk of lost mass?
That's a great question. So different stars, especially.
Repeat the question.
So the question was, what is a disk of lost mass? That's probably a bad phrasing of what, but essentially, stars lose mass for various reasons. More massive stars are more likely to lose mass. In fact, massive stars, one of the reasons they're really weird is all the way back to the. Here. When the sun evolves, it will evolve like this, go up to a red giant, and then it'll kind of collapse back into a white dwarf. It's very simple, it's very linear. Massive stars do a lot of weird things. Most stars will spend until the moment where they die, will evolve redwards. Massive stars, really massive stars, will lose enough mass that they can start evolving backwards, bluewards. They can start getting hotter again and do all kinds of crazy things. You have all kinds of weird stars. You got some called luminous blue variables. You got all these kind of weird shell stars. There are all these just weird blue stars that are also yellow stars, like fast pulsating yellow supergiants. There are all these weird stars that are doing all this weird physics because they keep losing their outer atmospheres, and then weird stuff is happening. So what's happening with the VE star, is it's losing some of its mass, and then it's rotating fast enough that that's getting whipped up into a disk right around the star. So it's really the star's atmosphere is getting stretched out into a disk because it's losing some of its mass, and then whipping it back up into a disk. Yes.
How long was it till they realized that seeing a spectrum shift could be used to identify how fast the star was either away or towards it?
Oh, that's a fantastic question. I actually don't know who figured that out. My assumption was that would be one of the things that was discovered in the turn of the 20th century. But I do not know that for sure.
Thank you for a wonderful talk. I just want another round of applause for both Dan and Ishan. Thank you guys for coming out. Our next Astro Talk is May 29th. I'll be there, please. It's gonna be great. And I guess I don't know when the last call was, but maybe get some more beer if you want to. But if not, we'll see you next time. And if you got trivia, if you want trivia, come get your prizes.